So we've been up to this point, we haven't really been talking about the mineral systems, how these elements form. Now we're going to start doing that. And so, yeah, I think I would just make him go to counseling just in general, regardless of what his favorite band's name was. But that's just me. All right. So as we said, we're talking about 10 elements in the abundant metals, right? And here we've got them outlined. All of these guys and this and this and this and this and this. So we're going to go through them and talk about how we find them in the earth. So we'll start off with the enriched low phosphorus banded iron formation, or BIF. We like to call banded iron formation BIF. Now you're going, what the hell? Who cares about the phosphorus? That actually is an important consideration. And so here what we're looking at is a map of global iron deposits, giant high-grade deposits. So these are the tonnages in the size of the circle, more than 1 gigaton, more than 15 gigatons. So you can see where the really big ones are in Western Australia, and that has a huge advantage for feeding the Chinese market, which we'll see is very important. And then these have an economic disadvantage because of the shipping costs. But there's a fair amount there. Yes, Clint.
Yeah, a friend of mine worked for Rio Tinto for a while, and they have a train that runs basically in a circle that never stops, that is loaded while moving, and it unloads while moving.
Wow.
And it just and it all goes to China, and then we get it.
Yeah, we get it in the steel. Yeah, the products. All right, so I tried to make some sense out of the deposits by plotting these two things: the ore deposit type, and we can talk about what kinds of ore deposits there are. And then the metal abundance type, which is basically economics, right? Abundant, scarce, rare, trace, precious. There's no information in those categories about how these deposits occur in nature. It's just telling you how likely it is you're going to find such a deposit. The effort here is to sort of subdivide the different geological environments at which these things form. And we'll talk about these. So magmatic, that's associated with igneous activity. Metamorphic, that's heating and squeezing and solid state phase changes, although fluids are also involved in metamorphism. Hydrothermal, that's, hot fluids moving around. And there's magmatic systems drive hydrothermal and metamorphic reactions. So there's a lot of overlap. But then we have things that are like sedimentary. And things that are sedimentary deposits like BIF, banded iron formation, and then things like placer deposits, which we'll talk about. There's deposits that form as a result of weathering. And then there are brines. Now, these, I would lump these as exogenic processes, exogenic mineralization processes. So exo is on the outside, so the Earth's atmosphere, the hydrosphere, the soil, biology, all of these things are the players in the exosphere, so that are associated with exogenic ore deposits. And I can distinguish those from endogenic, things that are happening inside the Earth in the absence of microbial activity or, the hydrosphere or the atmosphere. And I think that's useful. So these magmatic, metamorphic, those are definitely endogenic. Hydrothermal depends. Sedimentary, placer, weathering, and brine, those are all exogenic processes, right? So in one case, we're talking about how the Earth's exterior is interacting with the solid earth to make ore deposits. In the other case, we're just talking about the interior of the earth. Now, I've also color-coded these. Blue, the deposits are widely distributed, so we're not too worried about them, in terms of the politics or the economics. If we can't get it here, we can get it somewhere else. Red are deposits that are concentrated in one country, and or there are some geopolitical challenges that we should be aware of. And then a green, obviously, is a metal is important for the energy transition. And then also asterisks, because the definition of what a strategic mineral is in Canada does not map exactly in what the United States calls a critical mineral, I'm using asterisks. So you can see here that, BIF is an abundant metal. We've already talked about that. It's a sedimentary deposit. There's plenty of it running around, and neither Canada nor the United States is too worried about that from a strategy point of view. So what is the phosphorus problem? Why do we care that these iron deposits are in low in phosphorus? And the reason for that is got to do with metallurgy. So phosphorus, high levels of phosphorus in iron ore is detrimental. It follows iron during what they call downstream reduction, basically processing the ore into the metal that's going to be continually worked. So it makes iron phosphides that make steel brittle. So there's no commercial scale technology established to beneficiate the high phosphorus iron. So there's a new word. We should talk about what beneficiate means. It means to treat a raw material to improve its properties. So that's not too hard to remember. Beneficiation sounds like what it says. So there is a very much an emphasis on going after low phosphorus BIFs. And when we say low phosphorus, we mean the ore should have less than about 0.1% of phosphorus. Yes, Clint.
It sounds like something that you would get from the Pope.
Yes, I think so. Some kind of an excuse for your misled, your many errors of sins of omission and commission. You could be beneficiated. I think all of us.
Occasional homicides, sort of like, Benvenuto Cellini got forgiven. It's like, okay, these homicides were okay.
Yeah, it's understandable. So anyway, that's the phosphorus problem, which has got to do with iron. All right, so BIFs formed in the Precambrian there, and especially in the Paleoproterozoic, which was between about 1.6 and 2.5 billion years ago. And this was a result of the slow increase of oxygen in the Earth's atmosphere and in the hydrosphere, which converted iron, which is a very redox sensitive element, from divalent iron, which was soluble in water, to trivalent iron, which is not. So you're seeing that. If you see here, here's the atmospheric iron curve, greatly simplified. We're up here. This is only 10% of present atmospheric level. No, that's so we're here when this ends at 1,000 at the end of the Mesoproterozoic a billion years ago. So we're on the order of, looks like 8 or 9% of the present PAL, whereas back in the Archean, we were down at, trivial amounts of oxygen. So as this starts to go up, and there's a number of reasons. You still have your hand up, Clint? Do you want to make a comment, or is that just you doing a bob? You're muted.
I don't see my hand up, but then again, I'm having all kinds of problems with my internet here.
I will it'll go away, and if I see it come up again, I'll know you want to talk. So you can see that, this great proportion of BIF, banded iron formation, which is sort of dominantly the source of iron, but there are some others that we'll talk about. And then there's a fair amount in the Archean as well, especially the Neo-Archean, the last part of the Archean. Okay. So here we've got what a beautiful Ontario BIF looks like. I don't know. Have you guys ever seen that in the field, Matt?
The one on the left, yes.
Yeah. Well, the one on the right you might have seen in the field too, but that's actually, it's very hard to capture rocks in hairstyles, but this is probably the most successful example I've ever seen, and maybe other people have seen other ones. But
It may be the most successful. It's probably also the first.
I've seen some pretty good malachite.
Oh, that's true.
yeah. So the layering here in this BIF and in general is the black are the layers of iron-rich minerals like hematite, which is Fe2O3. And the red are layers of iron-rich chert, which is also called jasper. So, you don't really want jasper in your ore. You want a lot of the black stuff, right? So this is, I understand, how you youngsters talk. So say no more, fam. I have no idea what that means, but it sounds like that's what she's getting. All right, so here's kind of a cartoon of how banded iron formation forms. So here's a continental shelf, and you want to get away from clastic input because that will swamp out the iron. You want to get out in the basin where you're away from detrital sediments, so you're just precipitating and accumulating the material that is being produced as a result of the interaction of these iron 2 plus rich hydrothermal vents with high oxygen contents in the water column, which are going to be, near the surface. And then these will settle out. You'll see things in the literature about oxide facies or silicate facies or carbonate facies. The textbook doesn't really use that terminology, but you may see it in the literature from time to time. So one of the things that the iron ore mining community talks about a lot is supergene versus hypogene. And these are confusing terms. We use them a fair amount, but so the supergene, so here's the quote that this comes from. Exploration for BIF should concentrate on craton margin settings and Proterozoic sedimentary basins. Target generation should ideally be based on conceptual models, including syngenetic, hypogene, and supergene factors. So let's define those terms. Syngenetic is relating to or denoting a mineral deposit or formation produced at the same time as the enclosing rock or sedimentary rock. So, you can see that this is syngenetic. The sedimentation is going on when the ore deposit is forming, at least the primary ore deposit. Now, so in that sense, BIF are definitely a syngenetic deposit, if that makes sense. What do we mean by hypogene and supergene? So hypogene is something that's produced at depth, below the influence of the surface, and the supergene is above that, and it denotes the deposition and enrichment of mineral deposits by solutions moving downward through rocks. So is that about the way you would describe it, Matt?
Yeah. Yeah.
Okay.
Yeah,
So
supergene is the primary and supergene is the secondary, hypogene is the primary. Yeah.
yeah, okay. And we talk about that, a lot when we talk about what happens to ore deposits when they get close to the surface, because that interaction with biology, water, and air does stuff that is important. So, Clint, do you still have your hand up for a reason?
As far as I can tell, I don't have my hand up, but then again,
Okay.
if you can hear me, my internet doesn't even allow me to open a browser at this point. Teams is sucking up all of the water in the oasis.
You need a new computer.
Oh,
John.
it is a new computer. It's got
That's strange.
32 gigs of RAM, dude.
Huh.
Can you go back 3 slides?
Yes.
Yeah, the one with the oxygen. One more
Oh, I
slide.
see.
So why, I'm a little confused why we had this second big deposition of banded iron when the oxygen level was virtually the same as before, and
Well, so these are in ore deposits today. So if you recall, there has to be a basin where the conditions are right for forming this, and then it has to be preserved and exposed where it can be mined, right? So these blue curves don't tell you how much formed in a particular time. It's how much of that age formed. So maybe the answer to your question is that this was a time when sedimentary basins that were especially amenable to providing environments like this existed, and maybe the other times are when they didn't. Alternatively, it could be that this is a preservation problem, although preservation is rarely so selective in my opinion.
is there
You know,
something going on with continents colliding
oh,
or separating
oh
or anything
yes,
like
no,
that?
right. But so there's always this interpretation of the supercontinent cycle, which figures very, very prominently in the textbook, but I think it needs to be um, taken with a grain of salt. How far back in Earth history the supercontinent cycle is useful. The authors endorse it pretty much all the way back, and I think there's some issues with that. So I tend to downplay the role of the supercontinent cycle. But one of the things I would say is that this time period between 1800 and 2000 is very interesting, because it's, in my opinion, it's a time when there was an earlier episode of plate tectonics, and there was no plate tectonics in the later Paleoproterozoic and the Mesoproterozoic, in my opinion. And then this right here at the Archean Paleoproterozoic boundary, that's an interesting time, but that can be explained by that's when, according to this graph, the oxygen content of the atmosphere and therefore the hydrosphere was increasing rapidly. So it could be those two peaks have different causes, but neither peak would be possible without a rapid increase in the abundance of oxygen,
Thank
if
you.
that makes sense.
So the
As we
one at
as we say on Facebook, it's complicated.
the one at 1.9 is also, there's a lot of VMS deposits at that time, so you had a lot of hydrothermal input of iron into the oceans.
Yeah, that's a good indicator of hydrothermal activity, which this model implies, right?
Yeah.
This model may or not be right and we're sure it's wrong in detail, but it might be a useful model. And if it is, then it's saying, well, you've got to have nearby hydrothermal activity to have a banded iron formation. And that's a course in itself. Like everything we do. All right. So this is one of the most important iron mining regions in the world, is this part of Western Australia. I know it because one of our graduates left the United States, maybe 10 years ago, 15 years ago, and to try his fortune in Australia. And he got a job with an iron. We started off at a university doing a master's, and then got disenchanted with that and went into the mining industry in Australia and is doing very well now. But you can see where, yeah, Dean Tuck. Yeah, definitely. A past Geo Club president. I like to keep my eye on those. So anyway, these are where these mines are. I'm guessing, yeah, there's the BIF deposits, are these little black things. And then these are some towns. I'm sure they're not particularly exciting towns. But you can see these are Proterozoic versus Archean. So, I imagine the Hammersley group is Paleoproterozoic.
They're mining towns. Of course, they're exciting. Haven't you seen Paint Your Wagon?
Yeah. So anyway, there's a Hammersley mine. You can see these, massive operations. They are impressive. So these are the tonnages and the countries, right? There's the deposit name, there's the country, who owns it, gross tonnage, percent iron, megatons contained.
Can you
So,
go back to full screen, Bob?
oh, did I not? Sorry. Thank you. Demonstrating once again the value of team teaching. So, you can see that Hammersley district is huge. And then these two districts in Brazil are also very important. And then things sort of pale behind that. The USA's in the Mesabi range in Minnesota. That was very important in the early years of the United States. And I'm imagining this is one of the reasons that Trump signed an agreement with the Ukrainian government for minerals, this deposit. Canada, Wabush. I don't know that one. Do you know that one, Matt?
No, but there are others in Canada too. But
Okay.
yeah.
But you can see what they're going after, They want tonnage and they want percentage iron. You can see that the Hammersley district, these guys are big because they have a lot of tonnage and it's high, it's high percentage iron. So that's very attractive from economic point of view. So this is the global iron market. You can see that to a first order, it's Australia selling to China. Now there's sort of secondary hubs in Europe and in Japan and Korea. I'm not sure. I guess that's somewhere in maybe that's Iran or maybe that's Saudi Arabia. But you can see that economically, the same ore is going to be much more expensive to ship from Brazil than it is Australia. So steel production in 2021, China produces over half of the steel then, and then everybody else, India produces number 2, but basically a tenth of what China produces, as does Japan, the United States, Russia, and South Korea. So it's an abundant metal, but there's lopsidedness that is also kind of a geopolitical consideration.
The Pea Ridge mine is located near the town of Sullivan in southeastern Missouri. The mine produced high-grade iron ore concentrate, as high as 70% magnetic iron, from 1964 until 2001. This video shows a series of two-dimensional mine-level maps and cross-sections as three-dimensional panels within a rotating display. The original CAD drawings were generated by Doe Run Mining Company, the Missouri State Geological Survey, in the United States Geological Survey. The development history of Pea Ridge began in 1948 when a major magnetic anomaly was detected above the deposit. St. Joseph Lead Company drilled this magnetic anomaly as part of their lead-zinc exploration program and discovered a large magnetite body. The iron ore deposit is contained within a breccia at the center of a collapsed Precambrian caldera. Ore grades run as high as 70% magnetic iron, with 250 million tons of proven iron ore reserves. The deposit is open at depth. Subsequent production in a joint venture between St. Joe Lead and Bethlehem Steel began in 1964. Operation and ownership changed hands a number of times until mining operations ended in 2001. Ownership of the inactive mine changed hands from 2002 until 2019. In addition to iron ore, the mine hosts 3 different rare earth deposits. The current owner, Caldera Holding LLC, holds an active mining permit. Caldera has extensive hydrometallurgical studies and resource estimates of the tailings resource. The mine tailings resources accumulated over 40 years of mine operation. 120,000 tons of rare earth elements were deposited in the mine tailing lake that includes high level of neodymium, praseodymium, terbium, dysprosium, and recoverable levels of all other heavy rare earths and other valuable commodities. Caldera also has pre-feasibility studies supporting the reopening of the underground mine. Caldera plans to first develop the rare earth-rich mine tailings and then redevelop the underground mine. The second rare earth deposit is the phosphate gangue material that is distributed throughout the iron ore body. The phosphate is easily liberated as a byproduct and highly enriched with heavy rare earths. The resource may exceed 500,000 tons. In addition, 70,000 tons of rare earth elements including neodymium, praseodymium, terbium, dysprosium, holmium, lutetium, and scandium have been identified within 4 breccia pipes along the footwall in the eastern edge of the deposit. Thank you for watching.
Okay, now that's interesting because there's several things going on there. One is the Karuna, which enters into our discussion in iron, but what quickly became apparent is there's rare earth mineralization associated with these things, which right now is even more interesting than iron. And the other thing that's kind of interesting is that they're talking about mining the waste, the tailings pile. So the things that they threw away, you know, when the mine was open, is now the thing that might be make the actual deposit of great interest to the mineral companies. So that's an interesting perspective on something related to a couple of things, you know, associated mineralization and reworking of tailings piles. So now let's go to a terminology confusion alert. And that is, here we've got Kiruna's IOAs, which are, as your book talks about, iron oxide apatite deposits, and IOCGs, which are iron oxide copper gold deposits. These are, we talk about them as 3 different kinds of deposits, but you know, how we call something a deposit or not, that's complicated. So it's easy to see that a BIF is different than a Karuna because, you know, these are, Karunas are associated with felsic volcanics, you know, structurally complicated. They're different than BIFs, which are sedimentary. But now these other things with different names, you know, nobody's gone through and said, should this be 1 deposit type or 3 deposit types? So I guess what I'm trying to signal to you is, if you're confused, you're not the only one. But the book, Miller will talk about these in chapter 5. I mean, and they treat them, Karunas, as different than IOCGs. But yes, Tom.
I was just wondering, do you know if there's a paper out on the tailings stuff from this deposit?
No, you would have to dig in, and I encourage you.
Okay.
Let us know what you learn. So they have important differences. They are restricted to felsic volcanic host rocks, tabular strata parallel geometry, compared to the near vertical breccia pipes of most IOCGs. Karunas generally don't have much copper or gold, and they do have silicification, which is lacking in IOCG systems. So similars and differences. So this is, there's a lot of controversy about the genesis of Karuna type iron phosphorus deposits. Most recent workers proposing primarily magmatic origin, including the crystallization from an immiscible iron phosphorus melt in a subvolcanic or hypabyssal environment. They're now widely considered as products of the crystallization of iron-rich ultrabasic melts. This is kind of how they're showing it, that there's some kind of immiscibility. And what's puzzling to me is that the immiscibility places the iron on top, which doesn't make sense. You'd think the iron would sink. But you can see people are struggling with conceptualizing these deposits. But just in case some of you aren't familiar with immiscible liquids, these play an important role in mineralization. So it might be worthwhile talking about miscible versus immiscible liquids.
Miscible liquids. Liquids which mix together in all proportion and form a single layer are called miscible liquids. They are separated by the process of fractional distillation. Immiscible liquids. Liquids which do not mix with each other and form a separate layer are called immiscible liquids. They are separated by using separating funnel.
So that's kind of regular environment,
Miscible.
standard temperatures and pressures. So immiscible liquids at these high temperatures of where you have magmas, that's an area of significant interest. So here we've got a map showing global Kiruna/IOA/IOCG deposits. Now Olympic Dam is the big IOCG. That's a bonanza. There's Kiruna, right? There's P Ridge. And interesting, there's a number of them in Chile. These seem to be quite young, quite interesting. But that's sort of the global map of it. Oh, by the way, I should mention, you guys have got your project proposals due in 2 weeks. So those of you that haven't figured out what you're going to do, you better start working on that and consult with us. All right, so these are Kiruna IOAs through time. This is the temporal distribution. There's P Ridge. Oh, there's P Ridge. There's the Kiruna itself. I don't know what Grongsberg is. So, they're distributed through time. Notice the scale kind of changes range here. Okay, so I think, we're going to look at the Kiruna ore mine.
Descend into the depths of the earth. Join us on an unforgettable journey to Kiruna, Sweden, and explore the world's largest underground iron ore mine. This unique adventure offers a fascinating glimpse into the heart of Sweden. This isn't just a mine tour, it's a personalized travel experience. We'll share practical tips for planning your trip to Kiruna, including how to book the mine tour and what other exciting activities await you in this Arctic wonderland. From experiencing the magic of the Northern Lights to exploring the unique Sami culture, Kiruna provides a diverse range of experiences.
All right, and we, as we noted before, the Kiruna, the IOAs are associated with rare earth element deposits, because rare earths are concentrated in the phosphorus mineral apatite, which is just calcium phosphate. And the Swedish government-owned mining company LKAB, which runs Kiruna, has reported there's a very large deposit of rare earth metals they've discovered adjacent to the Kiruna mine. So these seem to be related, and that would be a useful thing because there's currently no rare earth mining in Europe. All right, so then the book goes on to bauxite. This is a very different kind of ore. It was first discovered by the French geologist Pierre Berthier in 1821 near the small town of Les Bas in the French Alps. Hope I pronounced that right. It is the result of extreme weathering of aluminum-rich rocks like granite. And bauxite is mainly composed of aluminum oxides, along with some iron oxides and silica, but minor alkali elements. It's bauxite and laterite are related. They're both products of extreme weathering. Laterite is iron-rich and bauxite is aluminum-rich. And these deposits are generally right on the surface. They have massive stratified, granular, or earthy structures. So there we have it. It's an abundant metal. It results from weathering, and the deposits are quite widespread. We could call it exogenic. It forms as a result of surface processes, as opposed to endogenic, which forms as a result of interior processes. So here's a bauxite mine. Aluminum is present in more than 35% of modern materials and equipment. Bauxite is not a mineral. It's not a rock. It's a kind of a soil that is aluminum ore. So this is a bauxite mine in Guinea, Western Africa, which hosts about a third of the best bauxite reserves on the globe. So here's some Australian bauxite. You can sort of see it's a weird looking rock with these pisolites. So a pisolite is a kind of a sedimentary rock made up of pisoids or pisoliths, which are approximately spherical concretionary grains, of different things. So that they're like ooids. So those of you that know what oolites and ooids are, these are like that, only bigger.
This looks like a rock someone would confuse for a meteorite.
Yeah, no, it's not a meteorite. All right, and so there's generally classified into two categories: lateritic bauxites, overlying igneous rocks, and karstitic bauxites, overlying carbonate rocks. So here you see sort of a typical deep weathering soil profile, with the bauxite in between, and then the sandstone at the base in this case. And the main factors controlling the genesis of lateritic bauxites are climate, vegetation cover, chemical conditions, groundwater circulation, texture and composition of bedrock, surface relief, formation time, and tectonic conditions. You need stability, not a lot of erosion. So here we've got the mineralogy and chemistry of bauxite. So the aluminum content can range 35 to 65%, usually not much silica. You don't really want that much iron in it. But the aluminous phases are gibbsite, which is just aluminum hydroxide, boehmite, which is a different kind of aluminum hydroxide, and diaspore, which is another kind. That will not be on the next midterm. So bauxite is documented from all the geologic ages, from the Precambrian to the recent, but the most important resources are mainly from the late Paleozoic and the Cretaceous and the Tertiary. So you can see the time scale showing when the big deposits were. They're in the Urals, the Mediterranean, different places. So the most significant bauxite producers globally are, in order of their economic significance, Australia is number one, China is number two, Guinea is number three, Brazil is number four, Indonesia, and India. So that's bauxite. Any questions about bauxite before we move on? Aluminum ores. All right. So now we're going to move on to something that is an awful lot like where we started with the BIFs. This is the enriched BIF hosted manganese deposits. So manganese mineral systems include sedimentary rocks, volcanic rock hosted hydrothermal types, and karst hosted deposits. The sedimentary manganese deposits are the most significant. They have a similar temporal evolution or distribution to iron deposits. Most banded iron formations contain less than 0.5% manganese, but there are some that are rich in manganese, where the manganese has significant economic value. And these, like the BIFs, formed before the great 2.4 billion year great oxidation event. And these are sedimentary type. So There we see it's an abundant metal, and it's widespread, and it's exogenic. It's a Canadian strategic mineral, but not a U.S. critical mineral. So here are the world's major producers of manganese. I think Ukraine, that was one of the things the United States was interested in, their deposits of manganese. All right, and then we're going to go on to oolitic manganese systems. But just to remind you what an oolite is, these are carbonate oolites we're looking at here. So oolites are sedimentary rocks, like we have on the right. That's an oolite. And these are formed from ooids, which are these rounded spherical grains of basically concentric layers. The name derives from the ancient Greek word for egg. Oolites are between less than 2 millimeters in diameter, and things bigger than 2 millimeters are called pisolites. So we have to imagine these manganese oolites. So that's oolitic manganese. It's not obviously sedimentary, exogenic, widely distributed. So this is a geologic sketch across the manganese system in Ukraine. So let's see, the manganese oxide ore is in red. Manganese carbonate ore is in orange. Manganese oxide carbonate orange, and then the manganese carbonate zone is here, right? And it's overlain by sands and shales, and underlain by Precambrian basement, typical sedimentary succession. This is what it looks like. This is oolitic manganese ore from the Nikopol deposit, and you can see the individual manganese oolites, right? This is one from China. So this is the chemical composition in weight percent. So these are different examples, different types of the ore. Very low in silica for the most part. The manganese varies a lot, up to almost 40%. So that's ore grade, right? And these are what they look like. So this is 1 centimeter down here. All right, so how do these things form? Well, manganese is redox sensitive. Manganese +2, like iron +2, is fairly soluble in seawater, but manganese +3, like iron +3, is not. And as soon as the conditions get more oxygen rich, the manganese +2 will convert to manganese +3 and precipitate. So a lot of people suggest that the Black Sea today may be an analog of the depositional environment of oolitic manganese deposits. So because the Black Sea is the upper part is oxygenated because it's always interacting with the wind, and that tends to keep this mixed. But below about 200 meters, you've got a oxygen depleted zone. And you look here at the manganese concentrations. There's very little manganese +2 up in this oxygen rich zone, but a lot in the water. So what they think happens is you've got mixing, and the oolites will form sort of at this depth where the transition between the insoluble manganese and the soluble manganese gets in there. Does that make sense? All right. Now, manganese nodules are a huge resource on the sea floor. So here we're looking at some manganese nodules, different kinds. They start growing from the middle and grow outwards. They lie on the sea floor. And these are maps showing where the significant fields with a lot of manganese nodules on the sea floor are found. So people have been thinking about mining these for a long time, but nobody's doing it yet. So we will talk more about manganese nodule in the section at the end of the class on seafloor mining. And instead, we'll move on to titanium, vanadium. Yes, Madison.
I was just wondering if there's any kind of latest information on how those nodules are formed. Is it just chemical reactions, or have they kind of established that it is biological?
Oh, I mean, now Matt knows more about this than I do. So Matt, why don't you answer that question?
Yeah, so the answer is both of the above. They form, so manganese nodules form diagenetically and hydrogenetically. So they form from direct precipitation from seawater in the tops, and then from below they can grow diagenetically. And the extent to which microbes are involved, I'm not 100% sure, but undoubtedly they are, because they're typically involved in most low temperature processes.
And how long does it take to form?
Also, some of these, like that one on the right, may have taken as many as 60 minutes. Well, it may date as long as 60 million years. They don't grow continuously; they grow episodically. But the thing is, if you look at the map of the globe, they're in the deepest part of the world's oceans where there's sediment starved. Because basically, if your sedimentation rate is too large, you just swamp it and you can't grow the manganese nodules. So they're in really quiet zones in terms of sedimentation.
And then if they're growing episodically, is that based sort of on changes to like biogeochemical cycles and like redox states or something else?
Yeah, great question. Global biogeochemical changes, yes. More specifically, I'm not. We'll know. We'll learn more about this, because I'll learn more about this later on when I talk about it in a future lecture.
Cool. Thank you.
Yeah.
All right. So then the book goes on to titanium, vanadium, magnetite, and platinum group elements in mafic layered intrusions. I guess it's in this section because titanium is definitely an abundant metal, but it lets us look at the Bushveld complex, which is a very important body in mineral deposits in general. So we're looking at a geologic map. We don't have a scale bar here, but it is worthwhile to compare the size of the Bushveld. It's about the same size as the U.S. state of West Virginia. So it is huge. And what you can see here is the surface map of a layered igneous complex. And on top, you have the granite. And on top of that is a sedimentary sequence called the Transvaal group. And below that, you have the intrusion zones shown here. So this is the titanium vanadium deposits. These deposits are concentrated in one country, and this one is in South Africa, and that's called a Canadian strategic mineral, not for the U.S. And this is an endogenic system, formed as a result of interior processes, not surface processes. So here's the Bushveld intrusions thought to have been the root of an immense volcanic field about 2 billion years ago in the Paleoproterozoic. So this is kind of a reconstruction based on an Andean volcano and sort of how they see that mineral system. So just imagine this body is, and the overlying volcanic field are on the order of the size of West Virginia. So there's lots of large layered intrusions, mafic intrusions around the world. You know, the Bushveld's down here, but you know, in the United States we have Stillwater and Duluth, and in Canada they have Sudbury. Sudbury's special because it's a layered igneous mafic intrusion, but it was triggered by a meteor impact. Set eels, I don't know much about Kiglapite, you know. Skaregard's sort of the one academically we know a lot. Muskox intrusion, Duke Island, quite a few. These systems are where academics and economic people like to interact a lot. So there we have the Bushveld showing the Marinsky Reef, which will be important when we talk about platinum group elements. And here we've switched gears and we're talking about global production of platinum group elements. And you see the role, how important South Africa is in that. USA's got a little bit of this. Russia's got a lot, but it's mostly South Africa. So this is the Marinsky Reef. Looks like a sedimentary rock. In a way it is. You know, it's an igneous sediment at the bottom of a magma chamber. And the people that mine this have lots of different names for it. This one is the Marinsky Reef is an igneous rock layer, which together with an underlying layer, the upper group 2 reef, UG2, contains most of the world's known preserves of platinum group elements, which include platinum, palladium, rhodium, ruthenium, iridium, and osmium. And then here's, we got some nice images of this contact between, you know, the anorthosite, very feldspar-rich rock, norite, it's feldspar-rich, but with a fair amount of orthopyroxene, and then pyroxene-rich, and then the chromatite, it is, that's where the PGEs are. And here you can see, you know, there's the chrome, there's the calcium, and there's the iron. So this giant layered intrusion has been worked out in great detail because of its economic deposits. So here's the upper magnetite layers and the lower magnetite layers. This is where you're going to have a lot of titanium and vanadium. And down here is where you're going to have the platinum groups elements. So they're in different parts of the intrusion. And you can see this intrusion is basically 9 kilometers thick. So you could spend your whole life just studying that thing. So your book spends a fair amount of time talking about this, mainly because one of the co-authors is in here. Not sure, I think that's probably him, Groves. And these are chromatite and anorthosite in the Bushveld, but the upper zone contains 24 magnetite layers that are concordant with igneous layering.
Nothing near the surface has been altered or bleached, oxidized or anything, or?
Well, Matt's actually been there. I never have, Matt. Maybe you want to take that.
Oh yeah, you get weathering at the surface for sure. But you still get outcrops of PGE rich material all around the Bushveld. I don't know much about the magnetite layers. I've had students working on the Marinsky Reef and chromatite layers for the last several years.
What were you guys working on them to do?
So we were working in the northern limb. So if you go back to just the outline map of the Bushveld, if that's okay. There we go. Oh, you can go. That little one's fine. Oh, there you go. So the stuff next to the north arrow, that's the northern limb. And so the other two limbs at the bottom are called the eastern and western limbs. And you can figure out which one is which. And so the Marinsky Reef is visible in the eastern and western limbs, and it's sort of typically about a meter thick. And that's what they mine is something that's around on average a meter thick. It's pretty amazing how they do it, because it's mostly done by hand. In the northern limb, what we were trying to figure out is there's the PGE rich portion, and so it was controversial whether that was Marinsky Reef or something completely different. So it was called the Platte Reef. And we had colleague and I had several students work on that. And probably it's equivalent to the Marinsky Reef, but it can be up to 40 meters or more thick. And it's sort of where most of the new mines are going in because it's so rich. I mean, this is the largest layered intrusion in the world, and it's the largest repository of platinum group elements in the world. It's a truly stunning geological phenomena.
Do people have a idea why it's so rich in PGEs?
I'm sure they do. I can't off the top of my head tell you what they are. I mean, it's related to the magmas. That
Yeah.
There's no question. So
Yeah.
yeah.
All right. Okay, well, let's watch a 6-minute video.
Hello everyone, we are back yet again to continue doing what we are best at. Let me officially welcome you to MJ School of Mining and Geology. Today we are dealing with the world's largest igneous intrusion known as the Bushveld Complex. Please do not forget to like, share, comment and subscribe to this channel so we keep producing this kind of a content. Stay tuned and enjoy the mysteries of the plate-like Bushveld Complex. The 2.05 billion years layered intrusion known as the Bushveld Complex is renowned as a source of vast quantities of platinum group elements, chromite and. The Bushveld Complex is a large igneous intrusion in South Africa, which is known for its rich mineral deposits. It is considered one of the largest geological features on Earth and is of great economic importance due to its abundant reserves of platinum, palladium, rhodium, gold, nickel, copper, and other metals. The vast size of 65,000 square kilometers and thickness of up to 9 kilometers of the Bushveld Complex make it an ideal testing facility for many petrological and orogenesis theories. Within this giant volume, the world's major resources of platinum and other platinum group elements, iron, titanium, vanadium, tin, and chromium are hosted. For over 90 years, it was the primary focus of continuous research from the moment PGE's mineralization was discovered. Nevertheless, there are still numerous aspects on which scientists need help to reach a consensus. The BC comprises main suites from the base, Rustenburg Layered Suite, Rashoup Granifier Suite, and Leboa Granite Suite as per Sachs, 1980 and the mother of the Bushveld, Professor Kinnaird in 2005. However, according to the other authors, there is a fourth group called Ruberg Group. This group is thought to a separate but related igneous complex located to the north of the Bushveld Complex. The complex covers an area of approximately 66,000 square kilometers in the northeastern part of South Africa. It is characterized by its layered structure, with different layers composed of various minerals. This makes it one of the largest igneous intrusions on Earth. The Bushveld Complex is characterized by its layered structure, which is the result of successive injections of magma into the Earth's crust. These layers are composed of various types of igneous rocks, each with distinct mineral compositions. The Bushveld Complex is renowned for its vast mineral wealth, particularly platinum group elements such as platinum, palladium, and rhodium. It also contains significant reserves of chromite, vanadium, and titanium. These minerals are of immense economic importance and have led to extensive mining activities in the region. Within these layers, various minerals were deposited as the magma cooled and solidified. The Bushveld Complex is particularly famous for its rich deposits of platinum group elements, PGEs, including platinum, palladium, and rhodium, as well as other valuable minerals such as chromite, vanadium, and titanium. The Bushveld Complex was formed around 2 billion years ago during the late Precambrian period through the process of magmatic differentiation. It is believed to be the result of a series of magma injections into the Earth's crust, leading to the formation of layered igneous rocks. While the exact details of the formation of the BC may still hold some uncertainties, ongoing research and geological studies continue to improve our understanding of this remarkable geological feature and its significance in the Earth's history. The formation of the Bushveld Complex is a complex geological process that occurred over millions of years. While there may be variations in theories and interpretations, the general consensus among geologists is based on the following principles. Around 2 billion years ago during the late Precambrian period, massive amounts of magma began to intrude into the Earth's crust in what is now the region of the Bushveld complex. This magma originated from the Earth's mantle, possibly triggered by tectonic activity or mantle plumes. As the magma intruded into the crust, it began to cool and solidify at different rates. This process, known as magmatic differentiation, led to the formation of distinct layers within the Bushveld complex. Different minerals crystallized at different temperatures, resulting in layered igneous rocks. The Bushveld complex is characterized by its layered structure, with alternating layers of different compositions and mineralogy. These layers include chromatite, anorthosite, pyroxenite, norite, and gabbro, among others. The layering is thought to be the result of repeated injections of magma into the crust over time, with each injection contributing to the formation of new layers. The layered structure of the Bushveld complex is a prominent feature. These layers are thought to have formed through processes of magmatic differentiation, where minerals crystallized at different temperatures as the magma cooled and solidified. The layering is evidence of the complex history of magma intrusions and subsequent cooling events that occurred over millions of years. Over millions of years, geological processes such as erosion, uplift, and deformation have exposed the Bushveld complex at the Earth's surface. The complex geological history of the region has been studied extensively by geologists, providing valuable insights into the Earth's crust and mantle dynamics during the late Precambrian period. Bushveld complex is of great interest to geologists and researchers studying igneous processes and/or formation. Its complex geological history provides valuable insights into magmatic processes, mineral deposition and the formation of ore deposits. Overall, the Bushveld complex plays a crucial role in the global mining industry and has a significant impact on the economy of South Africa. Its mineral wealth continues to attract attention from mining companies and researchers alike. The Bushveld complex is of immense economic importance due to its rich mineral deposits. It is a major source of platinum, palladium, rhodium, and other valuable metals, making it a significant contributor to the global mining industry. Thank you guys for joining us today. It really means a whole lot to us. Subscribe and comment on this channel to always be in par with our content. Until next time, cheers.
Hello.
I also wanted to say that the origin of the layering is quite controversial. Not everyone agrees on what it is, whether it's just crystallization the way they talked about, which is true of the Skaregard. Other people have talked about slurries or sills, so injections of magma along horizons, more permeable horizons. There's some age dating to back that up, although I'm a little suspect about the age dating, but it's really precise age dating. So, and it actually formed quite rapidly.
Okay, so now we started off talking about titanium, and we ended up talking about platinum group elements, which will show up later and that's kind of a confusion that happens with the fact that a lot of ore deposits, they're not easy to classify, and the Bushveld is apparently a good example of that. The economically most significant PGE, chrome, iron, titanium, vanadium, mafic later intrusions are of Neo-Archean to early Paleoproterozoic age. And we've already talked about world's primary PGE production. These are sometimes called orthomagmatic systems. And orthomagmatic refers to basically crystallization of minerals directly from a magma. And there aren't a lot of different kinds of ore deposits that do that. We're going to talk a lot about, we've already talked a lot about sedimentary ore deposits and weathering related ore deposits, but there are significant ones that are orthomagmatic, and this is definitely one, the Bushveld. So we don't really need to go into this early orthomagmatic versus late orthomagmatic stage. Due to the large size of layered mafic systems, measuring up to tens of kilometers across, or in the case of the Bushveld, even larger, they're relatively easy to find and delineate using geophysics. So when the ice is completely melted off of Greenland, they'll be able to find them. All right, now there's the Allard Lake ilmenite deposit in Canada, and Matt, I hope you'll jump in when I step on my own feet here. But here we've got that's the Adirondacks in northern New York. There's the St. Lawrence River. Kingston's over here somewhere, and this is exposed rocks of the Grenville, and the Allard Lake deposit is here. And what you can see, there's a lot of anorthosite intrusions, and there's a lot of ilmenite in there, which is ilmenite is a titanium iron oxide, FeTiO3. And here is the Allard Lake ilmenite deposit. It's sort of a view of it. Here's, what's been exploited is this small amount here, and then there's more to be exploited below it. And this is kind of a photomicrograph of ilmenite, orthopyroxene, and plagioclase in this, which is clearly an orthomagmatic deposit. Okay, so it seems that titanium, vanadium, magnetite, and PGEs have a certain amount in common with Karunas, IOAs, and IOCGs. And one might wonder how we could be more precise about the similarities and differences, which provides a opportunity for someone to do a student project on that. Okay, so now the next section in the chapter is ilmenite rutile rich, which means titanium rich beach sands. These are placers of a sort. So rutile, there you are on the right, is, that's rutile as it occurs in igneous settings, and just TiO2. And as it gets eroded, it gets rounded, and then it's heavy, so it gets concentrated in beach sands. So these are called heavy minerals. So heavy minerals is a way we talk about physically and chemically resistant minerals with a specific gravity of greater than 2.85 grams per cc. And they're heavy mineral titanium, zirconium, rare earth deposits associated with sediments in paleobasins, and that can be subdivided into paleo shoreline and marine placers, shallow offshore deposits, and fluvial and alluvial placers, especially gold, which we'll talk about when we get to gold. And the principal commodities of sand mining operations are zircon and titanium-bearing minerals, ilmenite, rutile, and leucoxene, locally with monazite and xenotime as byproducts. And these are an important source of the global titanium supply. And Australia is the world's leading producer of titanium, zirconium-bearing minerals from heavy mineral sands, producing about 53% of the world's rutile, 15% of the ilmenite, and 50% of the zircon in 2010. That tells you we haven't updated that lately, but. So the heavy minerals, these are placers, these are exogenic. The minerals themselves are formed as a result of igneous processes, but the concentration, the ore deposit, forms as a result of surface processes, so it's exogenic. So there's a good example of beach sand with containing layers that have concentrations of heavy minerals in them. So here we've got a schematic sketch of shoreline morphologies and heavy mineral sands in yellow. And this is taken as an example from the Murray Basin. It's a paleostrand line in Victoria, Australia. And there's also Aeolian heavy mineral deposits. And that's in the Eucla Basin of South Australia and Then there's another one in the Euclid Basin as well. And this diagram just shows you the different kinds of processes that can concentrate them. So these include weathering of igneous rocks. I'm not sure why they're showing that there. So erosion. I think these 1, 2, and 3 are related down here. So you weather igneous rocks, you erode them and transport them to the coast, and you deposit these grains as sand, and then they're sorted by the action of waves, tides, longshore currents, and wind. And you end up with packages of sediments that can have a lot of it. And these are just interpreting the environments at which these 3 deposits were formed. The Murray Basin here is seen as kind of a beach between a couple of headlands. The Euclid Basin is seen as something that's sort of a peninsula forming against a coastline where it goes into a deep embayment. And then the Eastern Euclid Basin, some kind of a barrier bar system. So here we've got chromatite layers in mafic layered intrusions. Now we're going to get back to bushveld. Chromatite is the only mineral source for the metallic element chromium. And chromatite is a rock that's mostly made of chromite. That's easy, right? Chromatite, chromite. And chromite is a mineral of the spinel family, consists primarily of solid solution iron, magnesium with chrome and oxygen. And it is mined from 1 or 2 types of rocks, layers in ultramafic or mafic intrusions like the bushveld, or podiform chromites in ophiolites. And more than 70% is produced from the mafic and ultramafic intrusions. So layered chromite is definitely magmatic, orthomagmatics, endogenic, and it tends to be concentrated in a single source, a single country. So, and it's a Canadian strategic mineral, but not a U.S. critical mineral.
Hey, Bob.
Yes.
Just for people's interest, there's a massive chromatite deposits in what's called the Ring of Fire in northern Ontario. Haven't been exploited yet, but they're so thick that it's quite controversial how the hell you get such huge thickness of like tens of meters thick of chromatite.
Are these in layered igneous bodies?
Yes, is the short answer. Beyond that, that's as far as my knowledge goes.
Yeah, I don't know anything about this.
Yeah,
Ring of Fire sounds like it's not a single intrusion.
No, I mean the chromatite thing is a relatively small part of it, but there's big vanadium deposits there. There's gold. There's all sorts of things.
Interesting. Yeah. There's a project for somebody. Is there much literature for where students could find something?
Oh yeah. There's literature out there, and I can put them on.
Yeah, there's a good project for somebody looking for one. Okay, so South Africa and Zimbabwe hold 80% of the world's chromite reserves, followed by Kazakhstan and India, other countries in here as well. And the bushveld again. So the chromatites are down here with Marinsky Reef and what's called the upper critical and lower critical zones. So, and I imagine they mine them together because they get PGEs out of the chromatites. Is that true, Matt, or not? Are they kind of separate?
Mainly out of the upper group. There are some they're defined by the chromatite layers, but the ones that are economic are primarily in the upper group, from my understanding.
Yeah, cool. Okay, now related to this are podiform chromite deposits. These are also magmatic in a way. These are irregular, lenticular, chromite-rich bodies that occur in the ultramafic sections of ophiolite complexes. So they're generally found in dunite or peridotite below the moho, near the contact of cumulate and tectonite zones in ophiolite sequences. And it's generally accepted now that the formation involves mantle melt interaction. And that's also magmatic. So here's an ophiolite section for those of you that don't remember that from tectonics. Here's the crustal section. This would be the moho right here. And pillow basalt, sheeted dikes, gabbros. And then down here we're in the mantle section. And then your chromites are sort of sitting in here, sort of right below the moho. And these are sort of typical outcrops of potiform chromites. Here you got layers of massive chromatite and Hartsbergite. So this is, you know, a 1 meter thick chromite body. And here's sort of disseminated nodular and massive chromatite in dunite. The dunite's the orangish stuff. Now I think we're going to end up with graphite-hosted carbon systems. These are metamorphic. So you'd go, graphite, that's a strange mineral, but it's becoming increasingly important, as you'll see. And most of it's from China, followed by India, Brazil. And economic graphite deposits are normally divided into 3 types: microcrystalline, vein-hosted graphite, and disseminated crystalline flake graphite. And they're formed by metamorphism. Microcrystallines formed by green schist faces, contact metamorphism, or regional metamorphism of coal seams. And then vein-hosted graphite deposits are associated with skarn. Skarn is where you intrude a pluton into especially carbonate rocks. And economic graphite veins are rare because they're usually pretty small, and they're only known from Sri Lanka. And then the disseminated graphite flake systems are the most common deposit type, and they occur in marbles, perronites, quartzites, and pegmatites, including Bissett Creek, Ontario. Do you know anything about that, Matt?
Nope.
So graphite is metamorphic, it's abundant, it's widely distributed, but it's important for the energy transition. So you're going, what? So it's endogenic. So here's a map of a mine in Tanzania. You can see how dark it is. And this is the global natural graphite production, again, dominated by China.
Can you go back one slide, Bob?
Yeah.
Go back one more. I mean, those ore trucks are, no, I was going to look at the photo. Those ore trucks are massive, right? That's not a normal pickup truck.
Yeah.
They're massive. So the scale of this mine is unbelievable.
Yeah.
Yeah.
Good point. Let's watch a video.
This man spends most of his life working inside the deepest mine in Sri Lanka. He's after a mineral that is now at the center of the global tech war: graphite. It's the largest component of batteries that power electric vehicles. And Sri Lanka has the purest graphite in the world. But today, China produces nearly 70% of the global supply. And in a controversial move, it recently restricted exports of the critical mineral to mega buyers like the US. So can smaller players like Sri Lanka step up to meet the world's growing demand? We went inside the biggest graphite mine in the country to find out. Lush rainforests surround the small village of Nithulpitiya, where Neil Suresh Abesikara grew up. The soil here is fertile, and many people grow their own vegetables. But the main source of income is graphite mining.
ඒකනේ මේ ගම් වල ඔක්කොම මේ ගෙවල් දොරවල් මිනිස්සු හදාගෙන ඉන්නේ පතල් ගිහිලා තමයි. වෙනත් ජොබ් නැහැ මෙහෙ.
One of the country's oldest graphite mines, Gahatagaha, is about a mile away. This elevator is what Neil places his trust in when he goes 2,000 feet underground. There are about 12 levels in the mine.
අටේ මට්ටමේ ගිහිල්ලා අයත් ඔය වගේ එකකින් අය යන්න ඕනි. එමෙ මෙති මට්ටම් 4-5ම තියෙනවා යන්න 2000 දක්වා යන්න. එහෙම තමයි යන්නේ.
It takes Neil about 15 minutes to get to the base. Down here, it's almost 100 degrees Fahrenheit.
බයත් හිතන අවස්ථාවල් තියෙනවා. දැන් ඒක අර එදිනදාම ඇවිල්ලා ගිහලා පුරුදුලා දැන් එහෙම දෙයක් දැනෙන්නේ නැහැ.
The Gahatagaha graphite mine is owned by the Sri Lankan government. It produces nearly 800 tons a year. The only way to extract the deposits is to blast the metamorphic rocks with dynamite. So Neil and his colleague Guruj Deshapriya have to set up this firing wire and dynamite.
අපි මේක පොඩ්ඩක් පලා ගන්න ඕනේ. මේකට වෙඩි බෙහෙත් කලවම් කරන්න ඕනේ. නැත්නම් මේක ලිමෙන්න බැරි නෑ.
They secure the ends with old papers. Then, Neil uses a drill to inject fluid into the walls, which helps stabilize them. They feed in the wires and dynamite and cushion them. It's important to fully seal the hole so the explosion can create an impact through the wall. They light the dynamite and move almost 1,000 feet away. Then, the men collect the graphite in these carts and move it out through the elevator. But if there's a power cut, things can get dire.
හදිසියේ විදුලිය විසන්ධි වුණොත් එහෙම අපිට ඉනිමන් වලින් තමයි එන්න තියෙන්නේ. මේ තියෙන්නේ මේ වගේ ඉනිමන් අඩි 2000 ඉඳලා මේ වගේ ඉනිමන් යන පාරේ හයි කරලා තියෙන්නේ. මුදුන්ට. මේවා තියෙනවනේ. මේකේ තමයි යන්න ඕනේ.
But there's so much more in these walls that miners can't access because their techniques and tools are nearly 150 years old. Like this small cart, which can carry 2 workers at a time deeper into the mine.
මේකට තමයි අපි වින්චේ කියන්නේ. මේකේ තමයි මේ ඩයිවර් මහත්මයා තමයි ඉන්නේ. මේ නම් බෙල් ගහපුවාම බෙල් 3ක් ගහපුවාම තමයි මේක පල්ලයට බාන්නේ.
Graphite mining in Sri Lanka can be traced all the way back to the 17th century. Its first documented use was for pencils. But by the early 20th century, British colonizers were mainly using it to make bombshells and cannonballs. Back then, there were nearly 3,000 graphite pits in the country. But demand for Sri Lanka's graphite dropped when World War II ended. Then, in 1971, the government nationalized the sector, and that led to even more neglect. Meanwhile, China started pouring resources into mining, leaving Sri Lanka in the dust. Today, there are 3 major graphite mines in Sri Lanka, including Gahatagaha, where much of the local processing is done by hand. Women sort and cut the graphite at small workshops. The purest kind has higher levels of carbon as much as 95%. And the women can identify it by simply looking at the texture, shine, and hardness. Currently, Sri Lanka produces about 3,000 tons of graphite a year, while China churns out nearly 850,000 tons a year. Graphite's main use these days is in lithium-ion batteries found in smartphones and laptops. And it makes up the largest part of any electric vehicle.
EV batteries have a positive side and a negative side, and graphite is that negative side.
The mineral is highly conductive, resistant to heat, and can store energy for a long time, making it ideal for EV batteries. That industry is expected to triple from $56 billion this year to $187 billion by 2032.
When you're looking at millions of vehicles being produced every year, you're going to need quite a lot of graphite to do that.
To keep up with demand, China is also making synthetic or artificial graphite. Manufacturing it is more expensive and harmful to the environment. Now, China is controlling who can buy this critical mineral. The government recently started requiring companies that export it to apply for a license first. And that would allow them to block some foreign buyers from countries like Japan, South Korea, and the US, which gets a third of its graphite from China. Experts say it's a power play as the two countries compete for dominance. China could use this to pressure the US on an array of political issues, from the control of Taiwan to the South China Sea. So now the US is looking into other sources. And that could be Sri Lanka's chance to step up. Companies like Ceylon Graphite are testing the material for lithium-ion batteries and have seen positive results.
It's absolutely a huge opportunity for Sri Lanka to take this material, this unique natural advantage that the country has.
But graphite from Kahatagaha is mostly used to make steel and lubricants. Neil says at one point, 1,000 people worked here. Today, it's less than 60. One reason is that wages are low. Miners make just 30,000 rupees a month, or nearly $100. Neil wouldn't tell us his salary. But when he clocks up from mining, another job awaits him. He also sells vegetables that he grows in his garden. While his wife prepares a traditional meal with vegetables, he helps the kids with their homework. He only finished high school, but he has bigger plans for his sons. The oldest is learning Korean and wants to study abroad. Neil hopes he can make it happen so that graphite mining is not the only option for yet another generation.